Hi kids, Mr. Dorfler here. Before we get started, this is the video that's going to be the kind of walk through the solutions for your homework problem from section 4, practice E, when we're talking about overcoming friction. And so before we get started, you might be wondering, isn't that the same shirt that he was wearing in the last video? Yes, you are correct, but it's the same day. I needed to make this video so I didn't forget. So here I am, a couple hours after. I don't remember when. I think maybe like almost an hour, 45 minutes after I made the last one. But I have been a video making fool today. Lots to get covered in all my classes. Anyway, don't want to take too much of your time here. I gave you the challenge of doing number 1 on page 141 to see how well you can get through these overcoming friction problems and combining everything that we've talked about thus far. And so now I want to go over it. Now, before we get started, this is how much space it took me to do this problem. So you're going to need some room to work here, okay? Granted, I have a little bit of space between, but whatever. Anyway, let's look at the question at hand, shall we? Page 141. If I can even get this here. Okay. Page 141. We're going to zoom in here to number 1 here. And we're going to rotate this. Rotate. Okay. So a student pulls on a rope attached to a box of books, and they must really like pulling books with rope, and moves the box down the hall. The student pulls with a force of 185 newtons at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms and a coefficient of kinetic friction, or it's always more fun to say mu k, between the box and the floor is going to be 0.27. Find the acceleration of the box. Okay, so we have a lot that we need to write down. Okay, we need to write down the applied force, which is 185 newtons. So it's always good to put this off to the side and label everything so you can immediately put them in the values into the formula. You have the theta, or the angle, above the horizontal at 25 degrees. You know the mass of the box of books of 35.0 kilograms. You know the mu k of 0.27. And you know, well, they don't tell you this, but you're going to have to eventually use it. But gravity the acceleration of gravity is 9.81 meters per second squared. Okay, so that is our problem. So let's do this step by step. Okay, I'm going to darken this a little bit. All right, so much like what we saw in our practice problem on the other day that I went over, we first need to, we could set up a coordinate system, okay, get over here, where we have this box, it's right here, okay, got a coordinate system here, here, okay, and that theta right there is going to be 25 degrees, okay. So first is we need to figure out the forces that are going to be applied in the X and Y direction, okay? So again, I'm kind of following the steps that was in our practice. And so we've got the F applied in the X, and we have the F applied in the Y, okay? And so we basically take the F applied, okay, for each. I'm just kind of work through these. And for the X, we're going to take that F applied and multiply it by the cosine of theta. And for the Y, we're going to take it multiplied by the sine of theta. Okay, so that gives us, we can put our numbers in here. Applied force, which we saw, sloppy handwriting, 185 newtons times the cosine of 25 degrees gives us an applied force in the X direction of 168 newtons. you're going to be rounding all the way through this problem, okay? So yes, I believe I rounded some a little bit there, but just a little bit. So 168 newtons. Now we're doing the same thing for the y. Take the 185. What is happening here? Newtons. That is a 5, I promise you. This time it's going to be times the, or multiplied by the sine of 25 degrees. And we get 78.2 newtons. So now we have our force that is applied in the x and y direction because of the student pulling on the rope at that specific angle. While we're here, while we're still early on, and knowing that I'm going to have to use this value here, I am going to go ahead and solve for the gravitational force, which is simply mass times acceleration. And so the mass of the box was 35 kilograms. And the acceleration on Earth is 9.81 meters per second squared. So our FG, which we're going to use here in a little bit, is going to be 343 newtons. Okay, you got our F applied in the X, you got our F applied in the Y, and you have our gravitational force. Okay, I'm going to run out of room here, so I'm going to erase. So if you need to pause and write this down or check your work, do so. Okay. Next is I am going to go into my parts A, B, and C that we saw in the practice one the other day. So in part A, we need to figure out we need to set everything to the equilibrium. All the forces, the sum of forces, set them to equal, or to 0, I'm sorry. And so what this means is all the vertical forces, I should say Fy, all of the vertical forces that are acting in this situation. So that means we have the normal force, we've got the F applied in the y direction, okay? And we also have the gravitational force. But remember, gravity is acting downward, so that's why we get the minus Fg and equal to 0. In this step, we are solving for normal force. So we need to rearrange this setup here to solve for normal force, and we just treat it like any algebraic equation. We get the normal force is equal to the gravitational force minus the F applied in the y direction. Okay? So now we can plug in our values. See, in that first part, we already calculated gravitational force because we are smart, intelligent people, and we already knew that we were going to use that. And so, excuse me, that means that we have 343 newtons minus the applied force in the y direction of 78.2 newtons. And so now in step A, we have a normal force calculated of 265 newtons. So now we can take that normal force and go to part B, where now we need to solve for our the force of kinetic friction. Okay, so basically we're going to take this equation, okay, Fk over Fn, and rearrange it to solve for Fk. So we're going to get Fk is equal to mu k times normal force. And so Fk is going to be equal to that 0.27 that we were given, multiplied by the normal force that we just calculated over here in part A, 265 newtons, and we're going to get a frictional or a kinetic frictional force of 71.55 newtons. And that's all for part B. The part C, in our final part, where we are actually going to be able to, what is happening here? Solve for the acceleration of the box of books, we are going to be using Newton's second law, okay? Where we're going to take the sum of all forces in the F or the x direction, set them equal to mass times acceleration. And all the forces that are in the x direction are the F applied in the x. And this time it's going to be minus Fk, because the force of kinetic friction, as I mentioned in the previous video, is always working opposite, or anytime friction is involved, friction is working in the exact opposite direction of the acceleration or the motion of the object. So that's why it gets the negative connotation here. Okay? But we are solving for acceleration in this step. So now we're going to rearrange this equation and have A in the x direction. You don't have to put that in the x direction, but I always like to because it tells us which direction the object is moving. Okay? Is equal to F applied in the x minus kinetic friction, that's a K. Let me fix that. K over the mass. So that means our F applied is going to be 168. We calculated that in the very first step, minus what we just did in part B, which is 71.55 newtons, and divided by 35 kilograms. And so, when we subtract and then divide, we get an acceleration of the box of, again, a rounded number of 2.8 meters per second squared. Now, because acceleration is a vector, we have to provide a direction. Now, the problem says down the aisle. And we often hear down the aisles a lot of times, okay? Now, when we say down the aisle, it is not saying that down is the vector direction. No, it's just saying it went to the other end of the aisle. So there's a couple of things that you could write. Again, we're not told that they're going west or left or anything like that. So we could say to the right, or we could also say down the aisle, or we could even say 2.8 meters per second squared in the positive direction. Okay? Any of those labels, which we have to have with this, any of those labels would work just fine. So there you have it, folks. That is your solution to number one. That was your challenge. Okay? So hopefully you all had good success, because you're going to see something along these lines, this type of problem, on your test here next week. So make sure you go over this again. If you have any questions on this, please don't hesitate to ask me. Until then, I'm going to sign off on this video, and I will see you later. Bye-bye.